Today we are going to talk about continuity. Continuity uses what we have learned about limits, and it is a basic fundamental criterion for several of our definitions and theorems in calculus, including the derivative and the antiderivative, the integrals. Let's take a look at what continuity is visually. So visually speaking, okay, if I have a graph of a function that looks like this function is continuous for all. I'm going to call this function f, and this function that I drew is continuous for all values of x. So this function f has no discontinuities. It's just continuous everywhere. Okay, let's take a look at this function. Well, I'm going to call this value of x a, and I'm going to call this function g of x. G of x is not continuous everywhere. G of x is continuous most places, but not at x is equal to a, because there's a hole there. So I would say g has a discontinuity at x is equal to a. This is a hole, and we call this a point discontinuity. So that is a point discontinuity, and it makes kind of sense that it would be called that. Might be better if it was called a hole discontinuity, but that's all right. Similar, right? Okay, and I'm going to draw a function h. So function h is going to have a vertical asymptote, and I think I'm going to call this x value a here too. And we could do a lot with this function. It's doing some things, and then it's going to go to infinity here, like that. And maybe this function is going to go here and do something like that. All right. So first of all, you don't have to draw arrows. If you don't have arrows, it's assumed to continue. If it was stopping, I would want you to draw a point there. Okay. So you don't have to draw arrows. If you want to draw arrows, you can, but you don't have to. All right, h has what is called an infinite discontinuity. So it is a discontinuity at x equals a, and it's called an infinite discontinuity at x is equal to a. So a vertical asymptote, only a vertical asymptote is an infinite discontinuity. Okay? Alrighty, so that would be a vertical asymptote called an infinite discontinuity. Alright, the last kind of discontinuity is when we have something like this that's happening at x is equal to a. Okay, this one, maybe we'll call this function j. J has what is called a jump discontinuity. A jump discontinuity, okay, at x is equal to a. Alright, so it makes sense that they would call that a jump discontinuity. So that's what these are the three types of discontinuities that you might see. A hole, which is a point discontinuity, a vertical asymptote, which is an infinite discontinuity, and a jump discontinuity. All right. Now, a hole or a point discontinuity is a type of removable. This is called removable. This is a removable discontinuity. Whereas these other two are non-removable. Okay? And of course this one has no discontinuities at all. Alrighty, so in class we're going to get together with a partner and we're going to talk about a definition. Knowing this, we talked about these, but we didn't really give a rigorous definition for a function to be continuous or not continuous. So you'll get together with a partner and try to come up with a definition for that. And then we would get back together and discuss those, and I would tell you what is commonly used for a rigorous definition of continuity in textbooks. Excuse me. Excuse me. Alrighty. I need to. Alright, back on. Okay, so a more rigorous definition of what it means for a function to be continuous at x is equal to a. So, f of x is said to be continuous at x is equal to a if and only if. Okay, continuous at x is equal to a if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, and that is equal to the function value at a. All three must be true for f to be continuous at x is equal to a. The limit from the left must equal the limit from the right, and that must equal the function value. So let's just come up here and let's designate an a point. The limit from the left is equal to the limit from the right, and that's equal to the function value right there. So this function is continuous at x is equal to a. For this point discontinuity, the limit from the left is equal to the limit from the right, but they are not equal to the function value. So that would be the definition of a removable discontinuity, or also called a whole, also called a point discontinuity. Alright? So f of x, a function has a removable discontinuity think whole, okay, at x is equal to a if and only if, okay, the limit from the left of a of f of x is equal to the limit from the right of a of f of x, but those are not equal to f of a. That would be a removable, a whole. Okay, what about the other kind? Okay, for the other kind, the limit from the left is not equal to the limit from the right. The limit from the left is not equal to the limit from the right. Even if these were both positive infinity, they would still not be equal. So the limit from the left is not equal to the limit from the right. So f of x has a non-removable discontinuity at x is equal to a if and only if the limit from the left of a of f of x is not equal to the limit from the right. And that would be an asymptote, a vertical asymptote, or a jump. Either one. Okay? Alrighty. Let's look at some examples, how you might be asked questions like this. Okay? So one question that I could ask you is to state the value or values of x, if any, at which a function has a discontinuity. So know this, a function has a discontinuity if it has a denominator, and if there's an x in the denominator that could make the denominator 0, then the function does have a discontinuity at that value of x. Regardless of if it's a whole, it's still a discontinuity. So since x equals 2 makes the denominator 0, g here has a discontinuity when x is equal to -2. Okay? There's a hole there. There's a hole there. Hole or asymptote makes your function have a discontinuity. Alright, so what about a piecewise function? Well, here's how we handle piecewise functions, dealing with continuity. Individually, there is no denominator here. So individually, this is continuous. There's no denominator here. Individually, that's continuous. So the only location where this might not be continuous is at the changing value, that 1. So we want to see, does this equal this when x is 1? If not, we have a jump. If so, it's continuous. So plug in this value of x for x in both of these equations, see if they are equal. So here we'd have a 1 squared plus 3, that is 4. Here we'd have a 5 times 1 minus 7, that's a -2. They are not the same. So that tells me that the limit from the left is not equal to the limit from the right. And if we wanted to justify, it doesn't say to justify, it just says to find. But if we wanted to justify, I would say the limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches 1 from the right of f of x. This is from the left, this is from the right. They're not the same. So therefore, f has a discontinuity. It's a jump discontinuity at x is equal to 1. Okay? State the value or values of x at which f has a discontinuity. Given this one, that's the exact same one. Okay, we're going to change this. We're going to change this. Okay, let's change this to f of x is equal to, we'll leave that top one. And on the bottom one, we're going to make it a 5x minus 1. Okay? So again, individually, these are each continuous by themselves. The only place that f might have a discontinuity is at the changing value in this case. So I'm going to put 1 in for x here, put 1 in for x here, see if they are the same. So if I do that, on this one, I'm going to have 1 plus 3, that's 4. And on this one, I have 5 minus 1, which is also 4. They are the same. So therefore, f is continuous for all values of x. No discontinuities. Okay? All right. Find the value of k that makes g continuous, given this piecewise function. Well, for g to be continuous, this must equal this when x is 1. So I'm going to put 1 in for x and solve and set these equal and solve for k. So 1 plus 3 must equal k times 1 minus 7. 4 must equal k minus 7. Add 7 to both sides. K must be 11. All right, little multiple choice question. Which of the following is continuous when x is 1? Let's take a look at f. For f, we only care when x is 1. We only care when x is 1. So when x is 1, right here, I do see an x minus 1, but this function only is valid when x is not equal to 1. So since it's only valid when x is not equal to 1, I can factor and reduce. So this factors to x minus 1 over x minus 1. One of these x minus 1s reduces, and we're left with just an x minus 1. So as x, excuse me, as we approach 1 from either the left or the right, we can substitute that 1 in. This will go to 0. So this goes to 0 when we substitute 1 in for x. So we're finding that limit. Okay? The bottom is always 1, not 0. So since these are not the same, f is not continuous at x is equal to 1. At x is equal to 1. I have something in my throat. Okay. So not continuous. We want it to be continuous. Let's go on to the next one. All right. Is g continuous at x is equal to 1? Well, the only place that g is not continuous is when x is negative 1. So is g continuous at x is positive 1? Sure. There's nothing about this that makes it not continuous at positive 1. So we found a continuous one. All right. For this one, individually, each of these is continuous on its own. I'm going to plug in 1 for this x, see what I get. Half of 2 is 1, plus this 1 is 2. That is equal to this other one, which means h is continuous at x is equal to 1. So we are also continuous there. So 2 and 3 are continuous. C is our answer. Okay. Number 5. We have a piecewise function, and they're asking what value of k makes f continuous. Well, for f to be continuous, this must equal this when x is 1/2. So I'm going to put x is 1/2 in and set those equal, solve for k. So we're going to have k times 1/2 cubed minus k times 1/2 minus 1/4, and that must equal 32 times 1/2 squared minus 2. Okay? 1/2 cubed is 1/8, times k will be k over 8. K times 1/2 is k over 1/2. 1/2 squared is a fourth. A fourth of 32 is 8. 8 minus 2 is 6. Okay? There are different ways to solve this. I always like to get rid of my fractions as soon as possible. So I am going to multiply both sides by an 8 because I know an 8 will take care of an 8, a 2, and a 4. So I'm going to multiply everything by 8. I'm going to get a k minus a 4k minus a 2 is equal to 48. This gives me k minus 4k, that's a negative 3k. Add 2 to the other side and we get 50. So k must be negative 50 over 3. We're going to change this one to 50 over 3. I made up a new problem and I kept the old answer choices. So our answer choice is B there, negative 50 over 3. Okay? Alrighty. I saw these little typos after I had copied everybody's packets. FYI. Okay. Too late to redo them. Okay. Number 6 here. The graph of g, a piecewise function, is shown on the right. Which of the following statements is true? G has an infinite discontinuity at x is equal to 1. So I'm going to x is equal to 1. An infinite discontinuity is a vertical asymptote. So do we have a vertical asymptote? We sure do. So yes, that is true. And we are looking for true. Okay? G has a non-removable discontinuity at x is equal to negative 1. So non-removable, that means a jump or an asymptote, a vertical asymptote. That's what a non-removable discontinuity is. So I'm going to x is equal to negative 1. Do we have a jump discontinuity there? We certainly do. So this is also true. Do we also have a non-removable discontinuity at x is equal to 2? Well, at x is equal to 2, there's our curve, there's our point. Do we have a non-removable discontinuity? That would be a jump or an asymptote? No, we do not have a jump. The limit exists. The limit from the left is equal to the limit from the right. We only have a hole. This is false. So only 1 and 2 are true. Which of the following has a jump discontinuity at x is equal to 3? A jump discontinuity. Okay, so individually, we're continuous. The only place we can have a discontinuity is when x is equal to 3. We're going to plug 3 in for x and see if they are equal. So I have 9 minus 12 plus 1, and I'm asking myself, is that equal to 1 minus 3? So 9 minus 12 is negative 3, plus 1 is negative 2. That is indeed equal to negative 2. That means that f is continuous at x is equal to 3. No jump discontinuity, so not f. Okay? G. Individually, those are both continuous. This is the limit from the left. This is the limit from the right. Correct? So to see if they are if we are continuous at 3, plug 3 in for x. See if the top equation is equal to the bottom equation. Here we have 15 is equal to 12, and that is not true. So we have a jump. Not equal. So we have a jump discontinuity. So yes, g of x has a jump. All right. Okay, you guys, for this one, look at what they have here. We have this function if x is not equal to 3. The only time the function has this one is if x is 3. And if x is 3, it really doesn't matter if they're equal or not. It doesn't matter, because when they set up the piecewise function like this, the most it could have is a hole. It's either continuous or it has a hole. Those are our choices. Neither of those is a jump discontinuity. So definitely not a jump discontinuity. And since they didn't ask us anything else, we can just say not H. So only G, so B would be the correct answer there. Alrighty, and that is continuity.